As you could tell from the title, today's lesson involves the kernel and the range of a linear transformation. Today's work should solidify and expand your knowledge of null spaces and column spaces. Let T be a linear transformation mapping vector space V into vector space W. Then the kernel of T, denoted by KERT, is the set of all V in sample space V such that T of V is equal to 0. So the kernel of the transformation is the set of all vectors in vector space V so that T maps vector V onto the 0 vector. The range of T, denoted by range parentheses T, is the set of all W in the vector space W such that T maps V into an element of W. Look at an example. TV is equal to AV for A is equal to 1, 2, -2, -4. Find the kernel of T and the range of T. Well, the kernel of T is going to be the set of all V such that TV is equal to 0, or AV is equal to 0 since T as a function of V is equal to AV. So we would have, well, we'll let V equal to V1, V2. So I have 1, 2, -2, -4 times V, V1, V2 is equal to the 0 vector. So I'm wanting all V such that AV is equal to 0. If I multiply, I get V1 plus 2V2, a -2V1 minus 4V2 is equal to the 0 vector. V1 plus 2V2 is equal to 0. A -2V1 minus 4V2 is equal to 0. Now, if we were to eliminate, we'd get 0 equals 0, so therefore we have a dependent system. I can write as V1 is equal to a -2V2. If we let V2 is equal to S, say, then V1 is equal to a -2S. So I would have V is equal to the vector 2s, and s. Or V is equal to s times -2, 1. So we can say the kernel of the transformation is equal to the span of the set consisting of the vector or the bases -2, 1. So this shows us that -2, 1 is a basis for V. So the kernel of T would be the span of -2, 1. Now we want to get the range of T. Well, the range of T is going to be the set of all W such that AV is equal to W. So I would have 1, 2, -2, -4, V1, V2 is equal to W1, W2. Or I get V1 plus 2 V2, the -2 V1 minus 4 V2 is equal to W1, W2. Or V plus V1 plus 2 V2 is equal to W1, a -2 V1 minus 4 V2 is equal to W2 when I equate the components. Now I can rewrite this as V1 times 1 -2 plus V2 times 2 -4, and we just say that's the vector W. Well, that shows us that W is a linear combination of the columns of A, because 1 -2, 2 -4 are the columns of A. So W is a linear combination of the columns of A. So what we need to do is we need to get a basis for the column space of A. Well, what I'm going to do to get a basis for the column space of A is to go back to A, and a basis for the column space of A would be the same as a basis for the row space of A transpose. So A transpose would be 1, 2, -2, 4. Row reduce, what I'm going to do is multiply row 1 by -2, add to row 2, -2 times 1 is -2, plus 2 is 0. -2 times -2 is now this should be 2 -4. I just wrote it down wrong. That's why it's not working out. Okay, so notice going all the way back, my column A is 1, -2, 2, -4. So if I do the transpose, it would be 1, 2, -2, -4 in the columns. So now -2 times -2 is 4. 4 minus 4 is 0. So then we know that the non-zero rows form the row space of A transpose. So they'll form the column space of A. So the column space of A is going to be 1, -2. So 1, -2, the set containing 1, -2, is a basis for the range of T. So I can say the range of T is equal to the span of 1, -2. Now we have a theorem. I'll prove the first part of the theorem and leave you to prove the second part. The kernel of T is the subspace of V, and the range of T is the subspace of W. So I'll prove the first part, that the kernel of T is the subspace of V. Now we've already established that the kernel of T was a subset of V, and the range of T was a subset of W. We've talked about that, but now we're saying they're also subspaces. Well, to be a subspace, then that means it has to satisfy the vector closure of vector addition and closure of scalar multiplication. Plus, we have to show that there is at least one element. So since T is a linear transformation, we know that T of 0 is 0. So if T is a linear transformation, we know that T maps 0 into 0. So therefore, there is at least one element. So 0 is in the kernel. Or the kernel of T is not empty. To show that the kernel of T is a subspace, we must show closure under addition and scalar multiplication. Let's let U and V be vectors in the kernel of T. So we know the kernel of T is not empty, so we'll let U and V be vectors in the kernel of T. Now T of U plus V is TU plus TV. That's one of the properties of a linear transformation. But if U is in the kernel of T, then I know that T of U is 0. And if V is in the kernel of T, then I know T of V is 0. 0 plus 0 is 0. Now, if T of U plus V is equal to 0, that means U plus V is in the kernel of T, and we have closure. Now, let's look at scalar multiplication. T of CU is equal to C times TU. This is one of the properties of a linear transformation. But since u is in the kernel of t, t of u is 0. C times 0 is 0. So t of cu is equal to 0. So that means cu is in the kernel of t. So we have closure of scalar multiplication. Let's do another example. And this time we're going to use derive. So TV equal AV, and notice that T is mapping 5 space into 4 space. 5 columns, 4 rows. So we want to find the basis for the kernel of T and the range of T. Well, basis for the kernel of T, we want A V is equal to 0. So if V is equal to, I'll just use A, B, C, D, and E, then I would want A 2, 2, negative 3, 1, 13, 1, 1, 1, 1, negative 1, 3, 3, negative 5, 0, 14, 6, 6, negative 2, 4, 16, times V, A, B, C, D, E is equal to the 0 vector. Well, what we're going to do first is to row reduce. So we're going to call in derive. And this is vector A. I simply entered A into derive. And now I told derive to row reduce A. So that means we have 1, 1, 0, 0, negative 2, 0, 0, 1, 0, negative 4, 0, 0, 0, 1, 5, 0, 0, 0, 0, 0, same one, times A, B, C, D, E is equal to 0. So I want a set of all vectors, A, B, C, D, E, such that A times V is equal to 0. So I have A plus B minus 2E is equal to 0. I have C minus 4E is equal to 0. I have D plus 5E is equal to 0. And of course, the last one would give me 0 is equal to 0. I see that A is equal to 2E minus B. C is equal to 4E. D is equal to negative 5E. Well, if we let E equal to S and B is equal to T, then the form of the vectors for the A vector is going to be 2S minus T. The B vector will be T. The C vector will be 4S. The D vector will be a negative 5S, and the D component, and the E component is S. I can write this as S times the vector 2, 0, 4, negative 5, 1 plus T times the vector negative 1, 1, 0, 0, 0. So we see that the kernel of T is a linear combination of these two vectors. So those two vectors would be a basis. And of course, the kernel of T would be the span of this basis. Now we want to find a basis for the range of T. Well, if we go back to the range of T, then we want vectors W such that AV is equal to W, or 2, 2, negative 3, 1, 13, 1, 1, 1, 1, negative 1, 3, 3, negative 5, 0, 14, 6, 6, negative 2, 4, 16, times A, B, C, D, E is equal to W. So we have 2A plus 2B minus 3C plus D plus 13E is equal to W1. If we let W be vectors W1 through W4. That would be A plus B plus C plus D minus E is equal to W2. 3A plus 3B minus 5C plus 14D is equal to W2. 6A plus 6B minus 2C plus 4D minus 16E is equal to W4. This would be W3 here. W1, W2, W3, W4. Well, we can see that this would be A times 2136 plus B times 2136 plus C times -3, 1, -5, -2 plus D times 1, 1, 0, 4 plus E times 13, -1, 14 it should be plus 16. Because we are coming across 6A, 6B, -2C plus 4D plus 16 is equal to the W vector. Or that W is a linear combination of the columns of A. So therefore, a basis for the range of T is the basis for the column space of A. Well, the basis for the column space of A is the same as the basis for the row space of A transpose. So let's go back to derive. Okay, here we have A. I row reduced A, and here we have A transpose. So you notice the first row of A is 2, 2, -3, 1, 13. 2, 2, -3, 1, 13, and so forth. So you look back in your notes and see that indeed I do have A transpose. Now if I row reduce A transpose, we get this matrix: 1, 0, 0, 8 sevenths, 0, 1, 0, 20 sevenths, 0, 0, 1, 2 sevenths, 0, 0, 0, 0, 0, 0, 0, 0. Well, your non-zero rows will form a basis for the row space. So the non-zero rows form a basis for the column space of A. So the non-zero rows form a basis for the row space of A transpose. So they will form a basis for the column space of A. So the basis will be 1008 sevenths (0, 1, 0, 20 sevenths) (0, 0, 1, 2 sevenths). Or since we're talking about a linear combination and you'd be multiplying by constants anyway, I could write it as 7, 0, 0, 8, 0, 7, 0, 20, 0, 0, 7, 2. Now I'm going to summarize some of the things that we discovered through the example. Let T be a linear transformation mapping N space into M space. And let it be defined by T of X is equal to AX. The kernel of T is equal to the solution space of AX equal to 0. The range of T is equal to the column space of A. Now these are the things that we discovered in the example. We've already used them because as we worked the example out, we discovered it was true. Now I'm going to give you just some definitions. The dimension of the kernel of T is the nullity of T, and the dimensions of the range of T is the rank of T. It should sound familiar to you. It's about the same thing that we talked about back with null set, column spaces, and row spaces. Okay, let's go back and give the nullity and rank of the transformation in the last example. Now the nullity of T is the dimension of the kernel. Well, we'll go back to the kernel. You can look back in your notes, but I'll show you. This is where we got the basis for the kernel. And if we have two vectors and a basis, that means that the nullity of T is 2. Now the rank is the dimension of the range, So here is the basis for the range. The range had 3 vectors, so the rank of T is 3. It's always true that the nullity of T plus the rank of T will be N, where T is a vector mapping Rn into Rm. So let T be a vector, be a transformation mapping the vector space V into the vector space W. And assume that V is an n-dimensional vector space. So V is n-dimensional. Then the nullity of T plus the rank of T will equal to N. Just like in our last example. We had the transformation mapping 5 space into 4 space. So the vector V was a 5-dimensional vector space. The nullity was 2, the rank was 3. 2 plus 3 is 5.